The next speaker is Professor Seongjeong Kim at Jilin University. His talk title is On Knots in SG cross S1 and its invariants. Please.
Thank you very much for the introduction. And first of all, thank you for organizers to give a chance to give a talk in knot theory in the conference, knot theory and applications. It is a big honor for me. Okay, let me start my talk. My talk title is Knots in S times S1, and it's parity-like invariance where the SG is the oriented surface of genus G. Okay, first, this talk is based on the following papers in the archive with some works in progress. My talk consists of 3 parts. First, let me talk some basic notions and motivations and basic notions and some basic theorems for links in surface times S1. And then we will introduce one important, simple but important information from knots in this 3 manifold. And then we will extend this information by using axioms, and we will show some examples. First, the motivation is the following. A fibered link in S3 is, roughly speaking, a link such that its complement is diffeomorphic to the surface times S1, where F is the Seifert surface of the link. And in 2013, by Mika Chrisman and Professor Marcel Rantroff, the relationship between virtual knots and classical links are studied by using fibered knots. The idea is the following. Let K union J be a 2-compound link where J is a fibered knot. Then K is a knot, actually a knot in the complement of J. And actually this is diffeomorphic to the Seifert surface of J times S1. Then when we consider the basic elementary covering over sigma J times S1, we can find the lifting of the knot K in sigma J times S1. Moreover, the linking number is equal to 0, then the lifting becomes a knot in sigma J times R, which can be considered as a subset of sigma J times 0, 1. It means that K becomes a virtual knot. In this manner, one can obtain the virtual knot from classical links, and one can expect that virtual knots can be used to study classical links. But our motivation is comes from the following. If the linking number is not equal to 0, then K hat is not closed. It means K hat is not a knot. Actually, it becomes an infinite link. But without covering, we still can obtain a knot in surface times S1. And we expected that this knot itself can give good and interesting information for us. So we are interested in links in S times S1, and we expect to use it to study classical links and some other areas. Anyway, because of that, we are interested in links in S times S1. And links in S times S1 is defined by a smooth embedding of this union of S1 into SG times S1. And if it has one component, then it is called a knot in S times S1. In this talk, we will present links in S times S1 schematically in this manner. Here, the cube it means the surface times 0, 1. And the connection between outside of cube means the arcs in S3 times S1. And now we define the equivalence relation for links in S times S1. Two links in S times S1 are equivalent if one can obtain from another by diffeomorphisms and destabilization of S3 times S1. Here, stabilization and destabilization are roughly speaking addition and deletion of handles from surface SG. And now let us construct diagrams for links in S times S1. The idea is very simple. First, we fix a point in S1, and we cut S times S1 at S3 times X0, and we stretch it. Then we can obtain a finitely many arcs and circles inside the SG times 0, 1. And then we project it onto the S3 times 0. Then we can obtain such diagram with points which were the boundary points of arcs. And now we replace these points by double lines satisfying the following property. For each point, there are two arcs, one of which is connected to the top side, and another one is connected to bottom side in S times 0, 1. Here we replace the point by double lines, so that the longer line is connected to the arc which is connected to top side, and shorter one is connected to another. And now if we give classical crossings and virtual crossings for each intersections, depending on the S3 times 0, 1, we can obtain a virtual knot diagram with double lines. Conversely, one can easily find the links in S times S1 from the virtual knot diagram with double lines. Moreover, one can prove the following theorem. Two links in S times S1 are equivalent if and only if their corresponding diagrams are related by finitely many moves described here. Here you can find the seven moves, which is actually generalized about Rademacher moves, and 3 more additional moves related to double lines. Here I want to show one interesting move obtained from the previous moves. Here we have a classical crossing. Then by moves, the fifth and first moves, we can obtain the right diagram. Actually, those two diagrams correspond links in S times S1. Locally looks like this. For left one, just we have two arcs placed like this. But for right diagram, we can there is a link. Locally looks like this. Actually, here and here, since there were double lines, the arcs are connected through outside of S100 01. It means through along the S1. But here, one can easily see that when we push this arc along this band, we can move. We can find the diffeomorphism between them in S times S1. Here, the point is, because of this move, one can say that where we lose will use over the information for links in SC times S1. But here, one good point is even we can change the over the information, we need to add the double lines, which means the rotation along S1. It means still the information how many times the arc rotates along S1 remains. Anyway, we can reformulate the moves by replacing first move by the previous move. And as it is asserted in the beginning of this talk, there exists a map from links in R3 with the 5 knot components to links in surface times S1. And one can show that converse is also possible. There is a map from links in S times S1 to links in R3 with the 5 component up to additional moves. And moreover, this theory looks similar to the virtual knot theory. And we can also prove one theorem, which is analogous to the Cooper-Bull theorem for virtual knots. It means we can find the minimal supporting surface for links in S times S1. Okay, before moving to the next section, I'd like to highlight again. Here, in this remark, we show that we lose over the information, but still we have the information, how many times the arc rotates along S1. And that information can be obtained by using diagrams. First, let us define the degree, which means how many times a knot rotates in SG times S1. For an oriented knot in S times S1 and a diagram D. For each double line, we give plus or minus 1 with respect to the orientation. More precisely with this rule. And then the degree of K is defined by the sum of all plus minus ones for all double lines of D. For example, in this diagram, there are 3 double lines with the plus 1, so the degree is equal to 3. But in this case, we can get a degree 0. And actually, this degree is exactly the same to the value of K of the class of K in SC times S1 with respect to the P star, where P is the projection map from SC times S1 to S1. It means this degree means the K, how many times the K rotates along S1 in S times S1. And similar thing can be done for each crossing. For a crossing C, we take a closed curve which starts from the undercrossings to overcrossing. Then the label of C is the sum of plus minus 1s for all double lines on this closed curve. For example, for this classical crossing, the gamma C is this one, and actually the label is equal to plus 1. But in this crossing, for this, in this diagram, for this crossing, we take gamma C like this, and the degree becomes the -2. And geometrically, this means the gamma C, how many times rotates along S1 in SG times S1. And those labels satisfy the following properties for randomized move 1, the crossing in this move have the label 0, and for two crossings in randomized move 2, they have same labels, and for three labels in randomized move 3, they satisfy this equality. And for the crossing in the crossing change with double lines, the labels, the corresponding labels satisfy this equality. And here one can notice that the properties which are satisfied by labels are similar to the parity axioms. And actually, one can see that if we consider the labels for classical crossings modulo 2, then it becomes the parity for virtual free knots. And if we separate the classical crossings by label 0 and others, then it becomes a weak parity. In this manner, for links in S times S1, even we lose overrun information, still we can obtain such parity-like invariant. Moreover, we expect that we can construct invariants for things in S times S1 by using such labels. I mean, the parity-like invariant for links in S times S1, and to use them to study classical links. But before that, I'd like to show one generalization for this parity-like invariant by using the axioms, which is called winding parity. Let A be an abelian group, then a winding parity on a diagram of K with the coefficient in A is, roughly speaking, the way how to give the value, the elements at the values to crossings, satisfying those conditions. Here, these conditions are derived from the properties satisfied by the labels in the previous section, and here, but here we replace -1 to a fixed element in A. Then we can easily see that the label, which is defined in the previous section, is actually satisfy these actions. Moreover, Gaussian parity is also a winding parity with abelian group G2 with a fixed element A is equal to 0. But here I would like to show one interesting example for winding parity, which is coming from the homology, first homology of S3 times S1. First, for a crossing C on the diagram, we can obtain arcs in S3 times 01, which is placed like this. And then we connect to the overcrossing and undercrossing with this orientation, and we take the closed curve gamma C. Then the gamma C is placed in S3 times S1 by if we consider the construction of the diagram. Then we give to the crossing the class of gamma C in the quotient group of first homology of S3 times S1, quotiented by the class of the K. And we call this correspondence homological winding parity. Then one can show that this homological winding parity actually winding parity. It means it satisfies the axioms for winding parity. valued in this abelian group with fixed element A. And from this homological winding parity, actually we can obtain the Label's and Gaussian parities, parity which were introduced few minutes ago. Then our next question was that, is there a universal winding parity? Here the universality means there is a winding parity with an abelian group such that for any winding parity, there is just a map rho from AUW to A, which commute here, like this. In other words, roughly speaking, every winding parity can be obtained from the this winding parity. Then the question is there a universal winding parity? Actually, yes, one can obtain, construct the universal winding parity very abstractly. We just take all possible diagrams from equivalent diagrams for a given knot K, and we take every vertices as a generator, and then we just quotient out by the axioms for winding parity. Then our next question was that, is it possible to describe this universal parity by using topological space? This is our partial answer. For an oriented knot diagram, for a knot in S times S1, first, by Kuper's theorem, we assume that SG has a minimal genus for K. And then from the diagram of K, we construct the topological space in the following way. First, we take place vertices on at each crossings and double lines. And then we connect the points which correspond to classical crossings. And then we attach a disk along the knot like this. And then we attach a disk along arc which bounds the two cells in the SG times SG minus K. It means, for example, in this case, there is the disk obtained from surface minus K. Then here you can find the corresponding arcs, corresponding cycle in this space. And then we attach a disk along this cycle. Then we can obtain a topological space CK. Then one can show that the first homology of this space is generated by the closed curve for corresponding to the classical crossings, which is obtained by connecting 2 points corresponding to classical crossings from under crossings to over crossing, and the cycles which were attached where double lines were. Moreover, they satisfy those properties. Actually, these properties are parts of the axioms appeared in appeared when we construct universal property. Moreover, for a two-knot diagram, we can show that the first homologies obtained from K and K prime are isomorphic. So we expect that actually from the construction of CK, one can see that it looks like a spine of the S3 times S1. So we expect that we can show these statements. Moreover, from our motivation, actually the double line looks like this. If we have such a fibered link, then by definition, the double line will be placed on this diaphotic surface of link, and moreover, by definition of the double lines, actually these double lines corresponds to such kind of, how to say, a twist with the boundary point of the fibered knot. That is, this looks like a fiber, the sliding along a second curving move with the framing +1 or -1. Moreover, in the action of winding parity, the fixed element which is related to double line can be arbitrary. It means maybe the double line can be related to such kind of links, a slide, which is a slide along a framed knot with framing 2. So we expect that our winding parity can describe the sliding second curving moves, and we expect to study three manifolds by using winding parities. And yes, that's all of my talk. Thank you very much.
Thank you. Do you have any questions or comment? Okay. Then let's thank the speaker.
Thank you very much.
Oh, Seongjeong. Seongjeong.
Yes.
Yeah. One question. Have you considered about braiding Alexander and Marcos theorem?
Yes. Actually, Alexander's theorem can be proved easily by because actually Rotuna can be proved.
It's easy.
Yeah, but for me, because of the existence of double lines, to be honest, I tried to prove the Markov theorem by using your idea, but because of some double lines, there is some ambiguities which is not resolved by myself. So I still trying to.
Do you know the paper by Sofia Lambor-Polo? Sofia.
Yes, L equivalence. Yeah, it is also in consideration.
Oh, I see. Thank you.
Thank you very much for the question.